This is a demonstration video looking at magnesium. Magnesium is a group 2 metal found on the periodic table. Magnesium is a low-density metal which does not naturally occur in nature. In nature, magnesium is often combined with other elements in an oxide or an ore. Here we have some pure magnesium metal turnings. As you can see, it's a silvery grey metal. We have placed some magnesium turnings into an empty old wine bottle, which we have connected to another glass bottle that has been set up to be a bubbler. We are adding pure water to the bottle containing the magnesium. Pure magnesium will slowly react with water to form magnesium oxide and hydrogen gas. Adding some uric acid or hydrochloric acid to the water acidifies the liquid, and the magnesium now reacts with the hydrochloric to form magnesium chloride and hydrogen gas. With the bubbler connected, bubbles can be seen to form. We are attempting to collect this gas in a balloon.
The initial amount of magnesium, which was reacting with the hydrochloric, was insufficient mass, so an additional piece of magnesium was added to the container with the hydrochloric acid to continue the reaction.
Once the balloon is full, it is carefully removed and tied. As you can see, the balloon is buoyant in air, suggesting possible hydrogen. To further confirm the presence of hydrogen, the balloon is lit. And sure enough, it goes with a bang. Eventually our magnesium finishes reacting with all the hydrochloric acid in solution, and now we are generating a white deposit which is magnesium oxide. Magnesium oxide is not soluble like the magnesium chloride in water, so to remove the magnesium oxide, the solution is filtered. The filtered solution is clear and colorless. To remove the magnesium chloride from solution, the water is evaporated. The white residue which is left behind is pure magnesium chloride. We are going to collect this magnesium chloride for a further experiment. In the next experiment, we are going to attempt to reduce the magnesium chloride back to magnesium metal. To attempt this, we are going to heat the magnesium chloride in a graphite crucible to melt the salt. Then we're going to pass a DC current through the molten salt to reduce the magnesium chloride and hopefully win some magnesium metal. With the salt in a mushy state, it didn't really melt, possibly forming magnesium oxide at elevated temperatures. A graphite electrode was submerged in the salt and about 4 amps of DC electric current passed through. There was a definite chloride smell when the current was flowing, possibly indicating that we are indeed forming magnesium metal. The reactions that are taking place at the cathode, magnesium metal is being reduced, and at the anode, chlorine is being oxidized to chlorine gas. You can see from this camera angle, we don't really have a molten salt, we have more of a mush, definitely some white residue there, which I suspect is magnesium oxide. After pouring out the remains in the crucible, a few metallic looking nuggets were formed. So we did reduce some magnesium chloride to magnesium metal, but not in a very effective manner. Another demonstration using magnesium is the reactive nature of magnesium in air. Here we are using a magnesium fire starting set. The first step is to position your main fuel. In this case, we are using some lollipop sticks. Then magnesium shavings are applied to the fuel using the back of the fire starter with a small hacksaw blade. We scrape along the back. Then the next step is to use the striker, which is on the other side of the fire starter. This is basically a mesh metal rod which generates sparks when scratched. Sparks are sent towards the powdered magnesium, which reacts, generating magnesium oxide, magnesium nitrate, and a significant amount of heat, which is what's igniting the surrounding material. In our final demonstration, we are going to make and use some magnesium flash powder. This was used in early photography and still used in theatre effects. Magnesium flash powder is a mixture of magnesium powder, sulfur, and an oxidizer. The oxidizer, for example, may be potassium nitrate or potassium permanganate. A fine powder is easily ignited. However, our powder was a little bit coarse, so it required an extended heat source to get the reaction going. Once the reaction going, our test subject was illuminated and a photograph was taken. This was a long exposure image, and thankfully our model stayed still. As always, please subscribe and thank you for watching.